Hello, my name is Manuel Diaz, and I will be presenting today our multi-scale LiDAR-Aided Perspective Transform network for real-time semantic grid prediction. For wheel-like robots, the bird's eye view or the top-down view can be a very useful representation since it represents the space or the plane which they are bounded to. This can be used for other tasks such as tracking or planning, since it can have a very rich environment representation of what's around the robot. For our method, we propose to use camera images along with LiDAR information in order to generate bird's eye view maps that are later decoded as the semantics of the environment around the robot. For this, we use the LiDAR point clouds and we project them to the camera reference frame or the camera image plane in order to get depth information to project each feature from each view of the cameras around the robot to generate bird's eye view maps. We do this following the camera pinhole model and the depth taken from the LiDAR projection down to the image plane for each camera. We perform this across multiple scales since CNNs gives us downsampling information about the images, and by projecting multiple scales, we can also populate even more the bird's eye view representation that can help us later decode the semantic representation of the scene. We decode the semantic representation of the scene from these projections of the camera information by using a simple CNN decoder and first adding up the two bird's eye view maps from each of the scales of the images, and then decoding them as an image in order to generate this this environmental representation with the semantics of the scene. For our experimental setup, we use the nuScenes dataset, and we predict a 100 by 100 meters grid at a resolution of 0.5 meters per pixel. This gives us a 200 by 200 cell space to which we project and we predict our semantic layout of the scene. Comparing to some of the state-of-the-art, we see that we outperform all of the camera-only baselines, and we outperform most of the camera and LiDAR baselines. For the two baselines that we get close, we note that our method is able to perform at real-time speeds, and these methods do not provide speed or an inference speed to which compare against. We see that our method as well, we are able to even further push its performance by adding a LiDAR-specific encoder to further process this LiDAR information that we were before only using to do the projection. Here we can find that using this encoder helps us enrich much more these feature maps, which in turn lets us predict a much more precise semantic grid segmentation. In adverse conditions such as rain or night, we see that the fusion of these two sensors helps us complement each other. Where, for example, in the rain condition, which will affect LiDAR, helps having the camera information, and in the night condition, which would affect the cameras, having the LiDAR can help us complement this setback. But overall, we see that the network is more reliant on camera features than LiDAR, since in the night we see our performance plummet much more than in the rain. In this work, we have presented a fusion approach that helps that generates semantic grids using camera and LiDAR information, and we address the projection problem by using the LiDAR information to help project the camera features. This project was supported by the CPS for EU project and Toyota Motor Europe. We also run our experiments on the Grid 5000. Here are some of our references, and thank you for your attention.